Hello class, this is Miss H. Welcome back to another notes video. So today we're going to be talking about acceleration and how to read distance versus time graphs, and also how to read our speed versus time graphs. So lots of graphs and a few practice problems is what we're doing today. So first things first, how is acceleration defined? Well, like last time, I've already kind of given us a hint. That is read as the change in velocity over time. Or you could read it as change in velocity divided by time. So first things first, you're like, change in, where is change in coming from? So this triangle is named delta, so that's the name of the character. But what it actually means is change in, so that's what you read it as. So just like how the equal sign means equals, delta means change in. Change in usually means like some kind of variable, the final minus the initial. So in this case it would be final velocity minus initial velocity. We'll get into that in a second. For now, let's go ahead and write our general acceleration formula. Our general acceleration formula is A, so A stands for acceleration. I love it, the beauty of it. Acceleration should be represented by A because it starts with the letter A. I like variables that make sense. Then we're going to say change in velocity divided by time. You could also put this as change in velocity divided by change in time. Whenever we went over speed and velocity, we were also talking about a change in time, but typically they already give us the change in time, so we just write it as t. And then I'm going to show you guys a more written out way of expressing acceleration. Acceleration is equal to the velocity final, or the final velocity, so that's a v with a little f, minus the velocity initial, also known as the initial velocity, so that's a little I to represent initial, divided by time. So this equation actually means the exact same thing as this equation, and we'll do some practice problems and we'll experiment around with these formulas. So without further ado, the first problem. A car is in a school zone going a constant velocity of 30 miles per hour. So I'm going to get my highlighter out again. We're going 30 miles per hour. That makes sense because we're in a school zone. Then 7 seconds later, the car is traveling 44 miles per hour. What is the average acceleration? Okay, so we're going to box what we want. Now let's look at what we've got. They give us 30 miles per hour. 30 miles per hour. So we have that per in there. That per, we know of it also as a division sign, so that's maybe mi divided by hr. So there's different ways to write miles per hour. So miles per hour, if you're driving, then it's a speed. It's, in this case, since we're talking about acceleration, we're talking about a velocity. So your car isn't swerving and turning around going crazy ways, it's just going straight. Constant velocity. So it says later on it's going 44 miles per hour, so we're given actually two velocities. So we're going to assume that we're going to use this formula. Well, this formula is really the same as this formula, but we're going to assume that we're going to use the more written out one because we're given two velocities. So first we have to find out what's the velocity final and the velocity initial. Well, we started off going 30 miles per hour, so that's going to be the initial velocity. Initial, if something is the initial move, the initial velocity, the initial time, the initial whatever, that means that it was there first. So our initial velocity is equal to 30 miles per hour. And then we have 7 seconds. Seconds is our time. 7 seconds. And then we have 44 miles per hour. That's going to be our final velocity, because that's the final speed that we're going. Then we want to know what the average acceleration is, so I'm going to write my A here. And then we're going to put the 3 question marks because we don't know what it is. And that's what I'm solving for. So first things first, we're going to go ahead and write out our formula. I'm going to write out the second formula just because it's already in that extended version for me, and I already know that I have an initial velocity and I have a final velocity. So my final velocity is 44 miles per hour. minus my initial velocity, which is 30 miles per hour. And then all that's going to be divided by 7 seconds. But something that you might notice is that this is in miles per hour. This is in miles per hour. This is in seconds. So now we have this dilemma of something's in hours. So our time up here is hours, but our time down here is seconds. So actually what I want to do is, before we move on any further, is I want to convert these seconds to hours. So I'm going to teach you guys a method called train tracks. If you don't get it the first time, that's fine. I didn't get it my first time going through. It actually took until college for me to truly understand what we were actually doing. But I think it's also because of the explanation that I was given. So hopefully the explanation that I give you guys helps you get it the first time. And if not, like I said, don't freak out about it. This is one of the more difficult concepts. That doesn't mean that you can't learn it. I'm trying to explain things so that they're not difficult. But like I said, don't feel bad if it's confusing. So here we go. I have 7 seconds. And then this is the rule. We're basically making a bunch of fractions. So it's not 7 seconds per hour or 7 seconds per meter or anything weird like that. So what I'm going to do is I'm going to draw this bottom line. And then I'm going to draw a dotted line. You don't have to draw a dotted line, but I like them being dotted. We've already established that anything divided by 1 is just itself, and I don't like having any blanks, so I just put a number 1 there. You could have left it blank, but it bothers me if it's blank, because then I'm like, is it 0? Because anything divided by 0 is undefined. So I fill it in with the 1. That way I know for myself that this isn't just some mysterious blank. So if there's seconds in my numerator, remember in fractions, the top number is a numerator, the bottom number is a denominator. If my numerator is in the units of seconds, then I know that this one, my denominator, is going to have to be in seconds. And then, because I want to divide, what I'm trying to do in this whole process is I'm trying to change my units from seconds into hours. Why am I trying to change from seconds into hours? That way I have the same time unit. So I'm only doing this because seconds are not the same as hours, and that's what they gave me in my problem. So I need an equivalency statement. So I don't know how many seconds are in an hour, but I know how many seconds are in a minute. So how many seconds are in a minute? 60 seconds. Good job. Alright, so now I have minutes. And if I do seconds divided by seconds, then again I just get 1. Anything times 1 is itself. So you can basically consider seconds gone. So now I have minutes. But I don't want minutes. I want hours. Do I know how many minutes are in an hour? And then I think to myself, I do know how many minutes are an hour. But then I say to myself, but do I put minutes in the numerator or do I put minutes in the denominator? These lines are basically like multiplication symbols. So you could consider that there's little multiplication kind of figures right here. And these are all little fractions in parentheses. And we're just multiplying equivalency statements. So if I want to get rid of minutes, I need it in the denominator. That way I can do minutes divided by minutes and get rid of that unit. Now, I know I want hours, and I can actually go directly from minutes to hours, so I'm going to put hours in my numerator. So, how many minutes are in an hour? Well, 60 minutes are in an hour. And then, my minutes divided by my minutes just give me 1, so now all my units, the only units left are hours. So I'm like, yay! I've successfully converted my seconds into hours. But this is quite a bit of arithmetic, so I'm going to let my handy-dandy calculator do it. We have 7 times 1, because that's what we have, divided by, I'm going to put a parentheses to make sure that everything in my denominator stays in my denominator, because if you just put divided by 1 and then times 60, then it'll divide by 1, and then it'll multiply by 60, which will give you a totally different answer than the parenthesis 1 times 60 times 60. So here we go. That's 0.0019 and then the 4 that goes on forever. So that bar on top of that 4 just means that the 4 is repeating and it goes on forever. This calculator only goes out so far, but it's implied that that 4 goes on forever. So now I'm going to come back over here, and instead of 7 seconds, I'm going to rewrite this. I'm actually going to I'll keep doing it directly below. Acceleration is equal to 44 miles per hour minus 30 miles per hour divided by 0.0. Oh, and that was supposed to be hours. And if you think about it, we only started with 7 seconds. It makes sense that we have such a small piece of an hour, because 7 seconds is really not a large piece of an hour. Let's see, 00194 with the bar, because it goes on forever, hours. And then now, using my calculator, I'm going to do 44 minus 30. And get that. I could have put it in parentheses. That's probably what I should have done. If I want to type it in all at once, there's different ways to do that. I just hit enter, but I'll go ahead and do it all in one go. That way you can see how. 44 minus 30, and then divided by, and then I'm actually going to go up and retrieve this answer. Then click enter. So I get approximately. So acceleration is equal to approximately. These squiggly equal signs means approximately. So if you're ever in doubt, you can put the squiggly signs so that you're telling your math teacher or your physics teacher or me or whoever, hey, I rounded, this is an estimation. 2 squigglies. That's a squiggly. There's a special name for it. I'll have to look it up later. But yeah, so about, oh, and then I forgot my units. So we have miles per hour divided by hour. And that's basically going to give us, I'll do some more work here. If we have miles per hour divided by hour, so miles per hour is equal to miles per hour, and then we have miles per hour divided by hours. We're just going to put a 1 in the denominator, because remember, hours divided by 1 is still hours. We're going to do our keep, change, flip, miles. Oh, I should put MI. Miles per hour. So keep, change to multiplication, flip 1 over hour. So we have miles per hour squared. Okay, so this is an acceleration unit. Notice that it's not meters per second squared, but it does follow the pattern. We have displacement divided by time squared. Anytime you see that displacement divided by time squared, you know that we're talking about acceleration. So that's just me circling the letter A, because I want you guys to know that we're talking about acceleration. And you can tell what you're talking about based on the units, if nothing else. So, coming back here, like I said, that's miles per hour squared. I'm going to box that answer. Alright, so that's that answer to that one. Now we're going to move on. A runner starts a race and after 5 seconds is running 15 meters per second. What was his average acceleration? I was supposed to pause and say, try to work this one out on your own. But since I read it to you, please pause the video now and try it on your own. Alright, if you have not paused the video, pause it now, finish the problem. I am going to go ahead and work this out so that you can double check your answer. A runner starts a race and after 5 seconds, so after only 5 seconds, this person is now running 15 meters per second. What was his average acceleration? So this one we don't have to do any unit conversions. This one is just more straightforward. So we're saying 5 seconds have elapsed. That's our time. Time is equal to 5 seconds. And then we say that he's going 15 meters per second. So that's his velocity. And since it's a runner and he starts a race, we can assume that his initial velocity, so VI, is equal to 0. And then the units are meters per second. And his V final is 15 meters per second. So that's probably the trickiest part of this problem, is recognizing that the initial velocity was 0 meters per second. But if he's a runner starting a race, then we know that his initial velocity is 0. So a lot of times if you're looking for acceleration and a problem only gives you one velocity, typically the initial velocity is just 0. Alright, and so like I said, final velocity was 15 meters per second. And we're looking for acceleration. We don't know what it is. Gonna write that formula again. Acceleration is equal to velocity initial, or my bad, velocity final, minus velocity initial, all divided by time. Since my velocity initial is 0, I can kind of use the shorthand one to just plug in our final velocity as the change in velocity, because the change from 0 to 15 is just 15 meters per second. But just to prove it to you guys, I'm going to go ahead and write out all the steps just so you can see it. Final velocity is 15 meters per second. I'm going to write meters over second because I'm trying to squish this stuff in. It's just another notation. This is the same vertically as it is whenever I write it sideways. So I wrote it sideways here, meters per second, and then I wrote it vertically here, meters per second. It means the same thing. Alright, so minus, and then we have 0 meters per second, and I'm writing it vertically to save time, over, and then our time is 5 seconds. So, what's 15 meters per second minus 0 meters per second? I'm glad that you asked. Anything minus 0 is just itself. So we're still going to have 15 meters per second. Notice that I switched back to the horizontal writing. This is just vertical writing. This is horizontal writing. They mean the same thing. Both of them are meters divided by second. Or by seconds. I'm not changing anything. And then divided by 5 seconds. So we still have that 5 seconds in the denominator. The only thing that I did was I got rid of the 0. Because if I subtract the 0, it's gone. That's it. If I add the 0, it's gone. That's it. It doesn't change anything. Like I keep saying. I just want to get that very clear. So now what I have to do is I have to say acceleration is equal to 15 divided by 5, that's 3, and then that's going to be meters per second squared. So just like how in this example we ended up with our hours being multiplied to each other, if we do the dimensional analysis on the meters per second divided by seconds, you'll see that the meters are going to stay in the numerator and the seconds are going to multiply in the denominator to ultimately give us seconds squared. Now, we're going to move on to this problem. It says a motorcyclist travels 17 meters per second before accelerating at a rate of 3 meters per second squared for 3 seconds. What is the final velocity of the motorcyclist? This one is a bit harder, I will admit to you guys. What I'm going to do for us right now is I'm going to write that triangle that we had last notes. That way you can see it again, because I know some people like the triangle, and so I like to provide you the triangle just to give you options. So here's my acceleration on the left, my delta V on top, and then my T on the right. So let's highlight what we're given. We're given 13 meters per second. That's important. We accelerate at a rate of 3 meters per second squared for 3 seconds. So what did they give us? They gave us a velocity. It doesn't tell us the direction, but since we're dealing with acceleration, we know that we're talking about velocity. So our velocity, and is this our velocity initial or velocity final? It says 17 meters per second before accelerating. So we know that this is our initial. It's what we started with. It's before we did anything. We had 17 meters per second. And then it says we accelerate at a rate of, so we know that that's our acceleration rate, and our acceleration rate is 3 meters per second squared. Also, the meters per second squared gives it away, that it's acceleration, for 3 seconds. Well, 3 seconds has always been our time. It's always going to be our time. So there's 3 seconds. And it wants to know the final velocity. So what we're actually looking for this time is the final velocity. So I recommend manipulating this formula if you're going to do it algebraically, or if you want to use the triangle. The triangle is really easy too. I'll go ahead and show you the algebraic way of manipulation. So we start off with acceleration is equal to change in v over t, which is acceleration is equal to change in velocity divided by time. And since I want to know the final velocity, I know that the final velocity is contained within this term, so the first thing I'm going to do is isolate this term. I multiply both sides by my time, so I get AT is equal to change in V. But then I'm going to break down my change in velocity to velocity final minus velocity initial, because that's the definition of change in velocity, is the velocity final minus the velocity initial. And I want final velocity. I forgot to box this. I want the final velocity. So if I want something, I have to isolate it. So I'm going to see what's going on around my final velocity. What's happening? Well, there's an equal sign, so I'm not worried about anything on the other side of the equal sign. But on the same side of the equation is minus velocity initial. Well, what's the opposite of subtracting velocity initial? It's adding velocity initial. Whatever I do to one side, I have to do to the other in order to maintain this equivalence. I'm going to put a big equal sign at the bottom. So that's going to be AT plus velocity initial is equal to VF. The other way that you could do this, you guys, is if you wanted, you could start from the very beginning. You could just start, I guess, here, or you could even start here. You could start with this equation. You could plug in all your knowns, and then you could solve for your unknown. Instead of manipulating the characters, if manipulating the variables is a little overwhelming, you could start there, or you could go back to our triangle. Our triangle would have taken you to this step of the AT is equal to delta V. Then you would have just replaced the delta V with these velocity final and velocity initial. You still would have had to add velocity initial to both sides, but it would have saved you a step. So that's just something that's out there. Now that I have my equation that I'm going to use, my equation that solves for the final velocity, I can go ahead and start plugging things in. So I'm actually going to take this up here. And I have acceleration, which is 3 meters per second squared. And since I'm trying to save time, I'm going to write it vertically again, meters per second squared. Okay, put that in parentheses. And then I have my time. My time is 3 seconds. And then I have plus velocity initial plus, and then I can put parentheses around this too, but I really don't need to, because whenever you're adding stuff, the parentheses don't matter. If there's a plus sign between parentheses, like you still have to follow order of operations, but it's just as if they're not there. So adding, like I said, the velocity initial is 17 meters per second. I'll go ahead and put parentheses around there just for consistency's sake. All that is going to be equal to VF. Alright, and now I take the first step. 3 times 3 is 9. And then if I do, you can put this over a little imaginary 1. Meters times seconds is going to give me 9 meters seconds divided by, and then denominator second squared times 1 is just second squared. And then, if I have seconds divided by seconds squared, well, I'll do that in the next step. I won't get ahead of myself. So I did that, plus, and then 17 meters per second is equal to VF. Remember, that's what we're trying to solve. I can't combine these because, well, I say I can't combine them because they're not like terms, but actually they are like terms, but they don't look like terms. So I'm going to help you make them look like terms before we combine them. So 9 meters seconds divided by seconds squared. If you're dividing variables, you look at the exponents. So the seconds has an imaginary 1, and then that has a 2. So you find the difference, and then wherever the bigger exponent is, that's where it stays. So the difference between 1 and 2 is 1. And then 2 is bigger than 1, so the seconds is going to stay in the bottom. And there's a little imaginary 1, like right there. There's also a little imaginary 1 on the meters. Both of those have an exponential value of 1, because anything to the first power is just itself. Alright, plus, and then we have 17 meters per second. So now they look like terms, right? Because we have meters per second and meters per second. Perfect, that's what I want to see. And if I add them together, then we get 26 meters per second is equal to the final velocity. And that's a pretty number. I like that. I'm going to box it to show that that's our final answer. We're done. We solved for the final velocity. Now, I want you guys to attempt this one by yourselves. I am going to give you 5 seconds to pause the video and attempt it. Alright, welcome back. Let's see if you got it right. And if you didn't, don't worry about it. We're all here to learn. A plane flying at 300 meters per second accelerates at a rate of 5 meters per second for 5 seconds. What is the final velocity of the plane? Final velocity of the plane. Oops, I highlighted that, but really I want to box that. They give me 300 meters per second. That's going to be my initial velocity. 300 meters per second. Then my final velocity, well, I don't know what that is, so I'm just going to put a bunch of question marks. And then my time is 5 seconds. And then my acceleration is 5 meters per second squared. And then I know what I'm looking for. I know what I'm given. Let's go ahead and write out my formula. Like I said, I'm going to start with the change in velocity is equal to acceleration times time. I just used the triangle, or you can start from the very beginning, and if you just multiply both sides by time, then you get the same thing. This is just flipped. So this one, it says AT is equal to delta V. It's the same thing as this. Just because I flip the direction, as long as the same things are on each side of the equal sign, they're the same expression. So it doesn't matter if you switch the left and right, so long as the left is on the left and the right is on the right, or the right is on the right and the left is on the left. Hopefully that made sense. So now that I'm here, I'm going to break this down into my velocity final minus velocity initial, because remember, that's the little definition of change in velocity, is the final minus the initial, is equal to my acceleration times time, but I want the final velocity, so I have to get rid of this initial velocity by adding the, oops, I don't know why I wrote a 4. That's supposed to be a V. That's VI plus velocity initial, aka VI. So velocity final is equal to acceleration times time plus the initial velocity. So let's keep on writing. We have acceleration times time. Acceleration is 5 meters per second. So I'm going to come down here, or I'm kind of running out of room, and I'm going to come up here. VF is equal to your acceleration is 5 meters per second squared, and then your time is 5 seconds, and then we're adding your initial velocity, which is 300 meters per second. Alright, and then first things first, 5 times 5 is 25. Then we have it over a little 1. Meters times seconds is meters seconds. Divided by seconds squared, because second squared times 1 is just second squared. And then we still have that plus 300 meters per second. We can simplify this by dividing out one of the s's, or subtracting our exponents. And so we know that we have 25 meters per second plus 300 meters per second. Our final answer of what velocity final is going to be 325 meters per second. Alright, that's the final velocity at the bottom. Now we're going to go to our graphs, and we're going to talk about what this means. We're going to discuss what a distance versus time graph is. So, whenever you think of distance versus time, I want you to think of speed. So we talked about speed in our last notes, and I'm going to help you recall to mind that speed is equal to distance divided by time. So slope, you might remember, slope is equal to your rise over your run, so your change in y over your change in x. So if we're thinking of it that way, your change in y is your distance, your x is your time. Oh my goodness, it makes so much sense. So, if this is true, if speed is equal to distance divided by time, and slope is equal to our change in y divided by our change in x, I don't think you can see that change in y, I might not have made it dark enough, hopefully that's readable, then that means, so if these are the same, if these are saying the same thing, then what does that mean about our speed? Our speed must be our slope. So I'm just going to draw an arrow, and I'm going to say slope of line equals speed. Now, if you look at this line, is the slope constant? Let's check. Up 1 over 1, up 1 over 1, up 1 over 1, up 2 over 2. Hey, this slope is constant. What does that tell you about the speed? That tells you that the speed is constant, because remember, our slope is equal to our speed, so we're going to write constant speed for the red car. Now let's look at the blue car. Let's see what kind of slope it has. It has like an up 1, up 2, up 3, over 1, 2, 3, 4, up 1, up 2, up 3, up 1, or over, sorry, 1, 2, 3, 4. Yeah, that's constant. We found the slope. The slope is the speed. So if you want to know how fast this is going, you could also do it that way too. It's going 3 meters every 1, 2, oh, whoops, I think I looked at the wrong one. 1, 2, 3 meters every 1, 2, 3, 4 seconds. So 3 meters per 4 seconds, or that would be 0.75 meters per second. So you could actually calculate the speed based on just finding the slope of a graph. So that's how we would do it. But I'm not going to focus on finding the slope of a graph. I'm just going to focus on what the graph, that's part of what the graph means, but I want to focus on a bigger picture right now. So this one, is the slope constant? It is. So the blue car is also at a constant speed. It's just at a constant slower speed. Because if you notice, the maximum time is 12 seconds. In 12 seconds, the blue car at a constant speed only travels 8 meters. At 12 seconds, the red car at a constant speed travels 12 meters. So we know that the red car is going faster. Now let's look at the green car. So the green car is kind of funky, okay? So we have a slope here of up 1 over 2, up 1 over 2. So that's like 0.5 meters per second. So right here the slope is 0.5 meters per second. How did I get that? I said that I go up 2 and then, oh wait, did I do it wrong? Oh, my bad. I meant that I go over 2, up 1, okay? And if I'm going over 2, up 1, then that means that, so we had change in y over change in x is equal to slope, which is also equal to speed. So remember that could mean is, so speed is slope is change in y over change in x is, our change in y was only 1, our change in x was 2, remember? So this is the change in x, this is the change in y. 1/2 is equal to 0.5, and then our units are meters per second. So this is meters, this is seconds, meters per second. Okay, so that's how fast we're going on this part. Then let's look at this. What is happening here? X changes by 4 seconds. But what's happening to my y? Am I increasing my distance? Am I decreasing my distance? No, it's staying the same. So what does that mean? Well, we can show it mathematically. So going back to this, if I do change in y over change in x, my change in y is 0. I'm not going up or down. And then my change in x is 4 seconds. So what's my speed? Oh my goodness. It's 0. 0 divided by anything? It's just going to be 0. So we have 0 meters per second. We're standing still. And doesn't that make sense? If you're walking, and you're walking kind of slow, but then you just stop, your distance isn't going to change because you're stopped. But time goes on because time waits for no one. So this is 0 meters per second right here on this graph. Now we can calculate this speed. It looks like I'm going up 1 over 1, up 1 over 1. Yes. So if we're going up 1 over 1, that's just that 1 meter per every 1 second. That's just 1 meter per second. So that's this speed right here. That speed is 1 meter per second. This speed is 0.5 meters per second. This speed is 0 meter per second. So what do we know about this car? Well, we know that it's changing speed. So this is not a constant speed. We can say that it stopped at least one time. Well, all we know for sure is that it stopped one time. So I'm just going to say stopped one time because that's what's visible in the graph. Now we're going to look at another graph. Alright, so this next graph, I'm going to be real with you guys. I stole this from the textbook, and it has speed versus distance, but I don't think that's right. It shouldn't be distance, it should be time. for what I'm trying to teach you. So we're just going to repurpose this graph. It's not distance, it's time. And it's going to be time in seconds. Or it could be in minutes. This is probably more likely in minutes, but that's fine. We're going to do speed over time. Alright, so now that we have our axes changed to their appropriate titles, I can tell you guys what a speed versus time graph is going to look like. So we talked about how the slope was related to speed, was related to other stuff for the distance versus time graph. Now that we have a speed versus time graph, what was our acceleration formula again? I'm going to write it right here. Acceleration is equal to change in velocity. And so I know this says speed. We're going to X that out too, and we're going to write velocity. You'll also see it written with a speed there, but for our purposes to be perfectly accurate, we're going to say velocity. So, acceleration is equal to change in velocity divided by time. Okay, so if our slope is still always our change in y over our change in x. So, if slope is equal to change in y over change in x, and then I told you guys that we could write a delta t right here, but it's kind of implied, inferred, stuff like that. So these are basically, you guys, they're the same. We're saying that our acceleration is equal to change in velocity over time is equal to our change in y over our change in x, which is equal to our slope. So you guys, I want you to draw an arrow pointing to the line, and we're going to say slope equals acceleration. Alright, so now you know that the slope is acceleration in this graph. So don't get it confused. Distance and time, we're talking about speed. We're talking about the slope of the line is equal to speed. Velocity and time, we're talking about acceleration. Slope equal to acceleration. Alright, so now that we've established that our slope is our acceleration, so this is a very positive slope. So what does that mean about our acceleration? Well, we're having a very positive acceleration. And if we're having a very positive acceleration, that means that we're gaining speed. So we're going to write gaining speed. And also, I want to come up with a scenario. We're going to say that we're a bicyclist. In this scenario, we're just riding our bicycles. Okay, so now we see we're gaining speed, we're doing good, and then we slow down to the point where our acceleration reverses. So at this part where acceleration reverses, what's happening? What could be happening? Well, using our imagination, we could be cycling uphill. So this is a common thing that I do whenever I'm biking. I'll be pedaling all fast because I know that a hill's coming up, but even though you gained all this speed to help you up the hill, you still slow down a bit, but you don't stop. Notice we didn't go down to a zero velocity, we didn't stop. After we get over that hill, now we're going downhill, so our acceleration, we're having some positive acceleration, so this is going down a hill. Right there. So that one's going down a hill, this one's cycling up a hill. And then, so now that we've gone down a hill, then our acceleration goes all the way to a stop. So what happened? Well, probably we were stopping maybe to cross the street. Maybe there was a stop sign. Maybe there was a red light, but we're bicyclists, so we don't stop at red lights. But you get the idea. Something made us come to a stop. But then, after a little bit of time, after we were stopped from like here to here, then we start going up again, but then we have this plateau. Now on the other graph, our plateau meant that our speed was 0. So what does the plateau mean here? It means that our acceleration is 0. So if I'm not accelerating, I'm also not decelerating. So what does that mean here? It means that I'm at a constant speed. There is no change in my speed, so there's no acceleration. Because remember, our acceleration is just our change in velocity over time. So if acceleration is equal to 0, then that means our change in velocity is equal to 0. Because let's look at our formula. Let's look at it mathematically. of acceleration is equal to the change in velocity divided by the time. We know that time is not 0. We see that seconds are passing. It's like 1 second of time passes and our speed doesn't change. And you can see that because we have our velocity graphed. So if there's 0 change in speed divided by our 1 second, I'll do this in meters per second. Oh, they did kilometers per hour. I'm going to change that too. We're going to do that in meters per second. I'm just going to steal this graph and rewrite all the axes. So, now we have acceleration of 0, which is our slope. Our slope is 0. So, look at that. It makes perfect sense. That's how we interpret this graph. If you guys need help or you have questions about this, do join me in the live session. I will explain things. Just ask. As always, do not forget your summary. I did read to you the notes and the sentence stems in the first video, so I'm going to assume that you watched that and that you listened to it. Same rules apply here.